So we could define the total number of microstates in the composite system as just a function of U1 only. Right? So here I'm kind of just talking in general equations, but to make this concept sort of stick, I actually want to start plugging in some numbers. So what we're going to do is we're going to look at how omega t changes as U1 fluctuates or changes, right? That's the sort of idea. So just to remind you, this is the sort of system that we're thinking about. We had two isolated systems that were then connected together such that they could exchange energy, but they can't exchange molecules or volume. All right? So system 1 and system 2 have their own initial energy, volume, and number of molecules. And so what I'm going to do is I'm going to, let's consider a system 1 where the number of molecules in it is just equal to 6. And the initial energy, which I'll call U1 naught, is just equal to, I'll say 1b, where this is just a constant. Okay? All right. So for system 1, those are the initial conditions. And for system 2, we're going to have 12 molecules, and it's going to start out at a higher internal energy. Okay? And so, if we calculate the total internal energy, it's going to be 1b plus 5b to give us a total of 6b. And so, in general, to get the number of microstates for either system 1 or system 2, it would follow this sort of equation. Right? So we have the total number of molecules in that system or subsystem divided by the number of molecules in that subsystem. And so the way I'll express that is I'll take the internal energy and divide it by B. Right? And so I mean not the number of molecules, but the number of energy states that are possible. Right? So we have the number of molecules that are in this energy state, and then that will be divided by the number of molecules not in that energy state. Okay? So this is an equation that we've seen before. Right? And so if we start plugging in the numbers, right? So for instance, let's say that U1 went from a value of 1b, let's say it has now fluctuated to a value of 2b, right? Just due to the energy transfer between systems 1 and 2. In that case, the total number of microstates for the subsystem 1 would be, we have 6 molecules, and we would divide it by 2, because that's the number of molecules that are in the, let's say, excited state. And then we would take 6 minus 2, take that factorial, because that would be the number of molecules not in the excited state. And so the total number of microstates, total omega for subsystem 1, would just be 15. In contrast, if we take a look at subsystem 2, right, its total internal energy would be UT, which is just 6b, and we would subtract off U1. And so the number we get is 4b. Okay? And so omega 2, in this case, would be 12 factorial divided by 4 factorial times 12 minus 4 factorial. And here we get a much larger number. So there's 495 for number of microstates possible in subsystem 2. And so if we calculate the total omega, we just take 15 times 495, and that gives us a value of 7,425. Okay? Alright, so this is a case for, if the system fluctuates and we get these energies for U1 and U2. But, of course, we could also do other combinations of U1 and U2 that give us 6B. So if we head to this table here from the textbook, we actually have different U1 and U2 value, or energy 1 and energy 2 values calculated out, right? And so if we see in the case where the internal energy 1 is 0, internal energy 2 is 6, the total number of microstates is smaller. And then if we increase it, eventually we will see some sort of maximum, right? In fact, the maximum we see occurs at the case that we were looking at before, where if U1 is 2B and U2 is 4B. Okay? So we see that here we get the largest number, and below it and after it, the values are lower. Okay? And so we'll write this out. Omega t hits maximum at U1 is equal to 2B. Okay? Alright, and so that's just for the case where U1 is equal to this value. We could also consider the number of microstates for every single possible value of U1. And so here, omega t for all of U1, we would just add up the sum of omega 1 times omega 2 for each energy value. And if we do that, we see that for any of the possible energy values, we have a total number of about 19,000. Okay? And so the reason I wanted to calculate this is because now what I want to do is calculate the probabilities of each of the different microstates. And so from the previous videos where we talked about the principle of a priori probabilities, we said that for a given macrostate, so macrostate of the internal energy of system 1 being U1, we can calculate the probabilities like this. So the probability for a given U1 value is just equal to the number of microstates for that U1 value divided by the number of microstates for all of the possible U1 values, right? Because, for all the U1 values and for a specific U1 value, there's this, they all satisfy the same total internal energy. Okay? In any case, we know that the omega total here, we could rewrite it like this in terms of omega 1 and omega 2. And this is just still divided by omega t for all of U1. Okay? So that's how we would calculate the probabilities. And so if we plug in some values, so for the case where U1 is equal to 2B, we have that 7,425 that we calculated earlier. And then we're going to divide it by the 19,000 that we estimated earlier. Okay? And so if we go through with this calculation, we see that for this value of U1, its number of microstates constitutes about 40% of all of the possible microstates that can exist here, right? So it actually makes up a significant chunk of the possible microstates. In contrast, if U1 is equal to 6b, and so in this case, we saw that there's only one possible configuration in which that could occur. So here it would be 1 over 18564, and here we find that we get an immensely tiny number. Okay? All right, and so this is how one would calculate the probabilities for a given U1 value over all of the possible U1 values. So this is how you would do it for the discrete case. But if U1 is a continuous value, if you're looking at a spectrum of energy values, then for calculating your omega t over all of your U1 values, you would just take the integral. Right? Because an integral is just the continuous form of taking a summation.